After talking about disaccharides, we can talk about polysaccharides. Poly means many. Okay. Poly means many. Okay, polysaccharides. Polysaccharides are used mainly for two reasons: to store energy in form of starch in plants or glycogen in animals, or for structure like cellulose. The trees, the wood you see, the paper mostly contains cellulose. That's a polysaccharide. Or chitin and pectin. Okay, I think chitin is found in the hard crustaceans, hard shell of the crustacean, and pectin also used as part of the wall, cell wall, like in plants. Alright, so let's look at starch. Again, it's mainly used for energy storage in plants, not in animals, in plants. And it's composed of amylose and amylopectin. So what you're looking at here that is boxed, that's the amylose part. Okay, so the amylose part is part of the long chain of the starch. Okay, amylose is a polymer of glucose. So this is a glucose here. That's a glucose. And this is a glucose pyranose. Is a six-membered ring. That's a pyran. This is a six-membered ring. That's a six-membered ring. And you see you have a glycosidic bond. Remember what we said a glycosidic bond is. Glycosidic bond is a bond between the oxygen of the anomeric carbon and an R group. Okay, so that's a glycosidic bond right there. Okay, and this also here is a glycosidic bond. Both of them are OR. Okay, so this is the anomeric carbon. We talked about anomers. It's anomeric carbon. Right now the oxygen is down, the CH2 is up. We usually call that alpha. Okay, we talked about that in an earlier lecture. So that's alpha. But look at the other ring. Look at the other ring. We do not need to assign the alpha anomeric carbon here because this is not anomeric. So this is the only anomeric. Anomeric carbon is carbon number 1, which used to be a carbonyl of the aldehyde. Okay, so we only point at that. Here we also look at the anomeric carbon. That's the glycosidic bond. These two is a glycosidic bond. But anyway, the oxygen here is down. On the anomeric carbon, the CH2 is up, so still that bond there is alpha. So you have the connectivity of the two glucose molecules, okay, making up what would have been a monomer of the amylose polymer. It's a polymer because we have an N here. Is connected. The two glucose are connected by alpha 1 4 links. So that's alpha, and you're connecting carbon 1 of ring 1 of glucose 1 and carbon 4 of glucose 2. So the two glucoses in amylose are connected by alpha 1,4 links in linear chain of up to 50 to 300 monomers. So this N right here, or this part, this unit shown in brackets, could be repeated 25 times, which means you have 50 monomers, or could be repeated 300 times. It could be repeated 150 times, which means you'll have 300 monomers. So this is just the chain length of the amylose, and it happens to be a maltose. So we know what maltose is 2 glucose combined. So that's the structure of starch. Briefly explaining it, it's usually complex than this. You learn much in biochemistry. Mine is to emphasize the linkages and to emphasize what makes the starch, because it's glucose molecules. Okay, so amylopectin is a polymer having alpha 1,4 links in linear chains with branches. That's the difference between amylose and amylopectin. Okay, so you have branches. What you can see here, these are the threads or linkages that are branched. And you can see here, you can look at this and call this a branch, a substituent. This was supposed to be an OH, but the H is gone. It's replaced by a dimer. Okay, a dimer of 2 rings. So that's branching. Okay, so amylopectin is branched. So you still have your alpha 1,4 link on the glycosidic bond. Here you also have alpha 1,4 links having the glycosidic bond. And so on and so on. The difference is just that you're gonna have branching. If you compare the structure of amylopectin and starch or amylose, it is gonna be branching in amylopectin. So that's the emphasis. And the branches might have sections of 25 to 30 monomers. The entire molecule will contain 300 to 5,000 monomers. So it's a very long chain. It's a polymer. Okay. So amylopectin, which might be part of the starch molecule, will be branched, but amylose is not branched. Both amylose and amylopectin make starch. Okay, so part of the polymer of starch is linear completely, that would be amylose. Part of it is branched, that would be amylopectin. Okay, so we've talked about starch used for storage. Cellulose is used for structural purposes, okay, to make the material or the structure stronger. Cellulose is a polymer of glucose with beta 1,4 links in linear chain of up to approximately 5,000 monomers. It's used for structural purposes. Starch was used for storage of energy in form of starch, okay, in plants. So cellulose gives fibers or makes fibers in plant materials, or it's the fibers in the plant materials like the wood, the leaves, the stem. If you see any fiber in there, then it's cellulose. Okay, so as you can see, this is our anomeric carbon. It used to be a carbonyl carbon, but this time the oxygen is tipped up. Look at this bond is tipped up. CH2OH is also up. Both of them are up. So you are looking at the beta anomer, not the alpha. We do not consider this as a numeric, so we're not gonna assign it with alpha or beta because it's carbon 4. We only do that for carbon 1. So you have cellulose unit, and we talked about this unit before. Let's see, where is it? Here is the cellulose. It's a product of hydrolysis of cellulose, and this is the unit looking at the chair. Okay, remember again, you have the beta anomeric carbon, or stereochemistry at the anomeric carbon. So you'll expect cellulose to contain cellulose. See, the names are similar. Going back to our slide, so cellulose containing the cellulose or bios unit, whichever you call it, with beta linkage of the two monomers. Okay, these two monomers again are glucose molecules. So you have a glucose, but the two glucose are joined by a glycosidic bond. These are glycosidic bonds. They are glycosidic bonds because you have an oxygen to a glucose to an R group. So cellulose acetate is used to make rayon, and nitrocellulose, which is used to make explosives. So cellulose has high value in the industry, in the market, okay, in material science. So other polysaccharides include chitin, similar to cellulose, with a C2 acetyl amino group, which means this group right here is on the second carbon of the ring. So here where the OH is, this is second carbon, so you would replace that OH with this group, then you get chitin. Okay, pectin is a linear polymer of galactose and alpha 1,4 linkages. So I'm just gonna mention those two just like that. If you have to take biochemistry, it's gonna be expounded. This is the survey organic. I'm not going to go deeper. It's looking complicated already for you. So both these two guys provide structural features. Okay, like pectin is used to strengthen the cell wall in plant cells. Ascorbic acid, it looks like a carbohydrate. Of course, it's a furanose. It's a 5-membered ring, and that's what we know as vitamin C. Vitamin C helps to prevent scurvy. It's a necessary ingredient or mineral for your body. It's a lactone. Remember, we said lactones are cyclic esters. Either a 6-membered ring, can be even a 4-membered ring, can be a 5-membered ring. It doesn't matter. It's a lactone. It's a cyclic esters are called lactones. So vitamin C is a polyhydroxylactone, which means there's many OHs. You see there's an OH here, so it's polyhydroxy and it's a lactone, with similarities to carbohydrates, because carbohydrates, of course, they make rings with oxygen in them. So, and you also have OHs on carbohydrate structures, like you see you have OHs on this monomer of glucose. So vitamin C is very similar to carbohydrates. It's weakly acidic though, because there's gonna be resonance stabilization. So if this is the structure of one resonance contributing structure of ascorbic acid, if you push these lone pairs here, the pi bonds opens, this opens up, we get this resonance. Okay, so when the bonds and the lone pairs resonate, you get these two structures, and that makes it acidic. Okay, of course it has some sweet smell, pleasant smell. That's a characteristic of esters. Esters smell sweet, like bananas ripening. That's an ester functional group right there. Okay. It's very important as an antioxidant. That's why you need it in your body. Whenever you drink it, it plays the role of a sacrificial molecule. It reacts with any radicals in your system and leaves the important water-soluble compounds in the body to do their job. If the vitamin C is missing, then those important molecules, biological molecules in your system will be reacting with the radicals in your system, and then they will not play their role, including enzymes and so many other compounds that are water soluble in your system. Okay, so it's very, very important that you have enough vitamin C, so it plays the role of a radical scavenger and protects other water soluble compounds in the body from doing unwanted reactions. So if you expose ascorbic acid, vitamin C, in air contains oxygen. If you have oxygen, you're gonna expect there's gonna be oxidation. Remember, we defined oxidation as addition of oxygen, but we also defined oxidation as removal of hydrogens. Okay, so in this case we are removing hydrogens. This hydrogen and that hydrogen will go, they are missing here, so then this molecule is the oxidized product, oxidation product. And that's what vitamin C does in presence of oxidizing agent in your system. Okay, that will conclude chapter 16, and that concludes our class this semester. You will have the rest of the 2 days to review your material. I'll try and do a review of exam 1 and 2 and send the videos to you so that you can study for your test. Your test is as posted in your syllabus. Go look at your syllabus, schedule your time. The date did not change. I cannot change it, only the university can change it. Okay.